So was the 8-7 part okay, where we're just writing the 3D vector equation from the line? That should have been pretty easy, right? The only thing that was different was getting the direction vector, but getting the direction vector is easy, so there wasn't too much to do. I'm assuming most of the problem was kind of in the 8-8 piece. So this, what I did is I started by giving you like a flow chart to kind of figure out what situation we're in, because there's 4 different outcomes you can have for the interaction of 2 3-dimensional lines. So the first thing we check is, are the 2 lines parallel? And you do that just by seeing if the 2 direction vectors are scalar multiples of one another. So basically, is there some number k I can multiply the direction vector of one to get the direction vector of the other? So presuming that it is that case where the slope vectors are scalar multiples, then we'd want to check to see if the lines are coinciding. To do that, all we need to do is check to see if a point from one line is also a point on the other line. So the easiest way to do that is take the point vector from one line and see if that point vector is on the other line. And it doesn't matter whether you take the point vector from R1 and see if it's on R2, or you take the point vector from R2 and see if it's on R1. Or you could use some other point that's not the point vector. I don't know why you would do that, but you could. So if that point vector from one line is also a point on the other line, that tells you that the lines are coinciding, because if they're going in the same direction and one of the points is the same, then it's going in the same direction. It's going to cover all the same points, right? If that point vector is not the same, then we just say the lines are just normal parallel, like there's going to be no interaction or no intersection. Okay. If we found the 2 slopes were not scalar multiples, we need to check to see if the 2 lines are intersecting. So basically, we just set the 2 lines equal to each other. That's going to result in a system of 2 equations that we need to solve. When we do that, though, we have to be careful, because we have 3 equations but 2 variables. So when you make your system, you're only going to pick 2 of the 3 equations, and you'll solve that system. But the answer you get, you still need to check in the 3rd equation to make sure that it still works. Okay? If that all happens, if you can solve the system and get a solution, and that solution checks in the 3rd equation, those 2 lines are intersecting, so you can use one of those values for S or T to find the point of intersection. If there is no solution, or the solution doesn't check the 3rd equation, so if the system has no solution, or if when we plug that solution back into the 3rd equation doesn't work, we'd say that these lines are that non-parallel, non-intersecting situation that we drew this picture of, right? Where the 2 lines are in 2 different planes but aren't parallel, like there's not a one plane that we can find that, oh yeah, both those lines exist in the same plane, and they wouldn't intersect here. There's no plane in common between the 2 lines that we've drawn here. So that little flow chart kind of just tells us the decisions that we need to make and the things that we need to check. So my first example here were these 2 lines. So the first thing I checked was to see if one line or one of these direction vectors is a scalar multiple of the other. So basically, it was easy to see that if I multiplied the direction vector for R2 by -4, I get the direction vector for R1. I didn't really bother to write a lot down there, but I can do that kind of on site. Everybody see that? Now, will they always be that obvious on site? No, Mr. Kulik's a sneaky jerk and might include like a fraction or something in there, like where he is able to disguise that, yeah, it's the same thing, but like all these even numbers turned into odd numbers somehow or whatever, and like he used some sneaky fraction or something, and don't put that past me. But right now we'd conclude that, okay, so we answered yes to the question, is one direction vector scalar multiple of the other. So now we're just going to check to see if the lines are coinciding. So I'm just going to take the direction vector from one of them and plug it into the other line and see if that direction vector is on that line. So I basically took the 307 and plugged it in for R1 and then I'm going to see if there's a value of t that makes that possible. So basically I just take the x component, so I need 3 to equal 2 plus 4t. I need 0 to equal 3 plus negative 12t, and I need 7 to equal 3 plus 16t. And in each case, when I solve that, I get 1/4. So that tells us that 307 is a point on R1. And since the direction vectors are scalar multiples, and a point from one line is also on the other line, we know that those lines are coinciding, that they're really just the same line. Does that feel okay on what we did there? Okay. So my next example have the same thing here. So 2 lines. First thing I want to do is to check to see if the direction vectors are scalar multiples. So I just see, okay, is there some value of k that I can multiply the direction vector -6, -9, 2, and get the direction vector 4, 5, -3. This is pretty easy to see that no, there's not. For the x components to be the same, k would have to be -2/3. For the y components to be the same, k would have to be -5/9. I'm not even going to bother with the z component because I already know that there's not a single value of k, so I just stopped right there. So I know that those 2 lines are not parallel. So if I go and I look down here, I need to check if the lines are intersecting. And I do that by setting the 2 lines equal to each other. So that's what we did here. And just like before, I did the vector operation. So I did the direction vector times t, and then added it to the point vector. So 2 plus 4t, 4 plus 5t, 1 plus -3t. And I did that on both sides. Cool. And then I moved the variables onto one side and the constants on the other to get this system. Everybody's okay with that? So like I added 6s over here and then subtracted 2 over there. So I get 4t plus 6s minus 4. Cool. When I write my system, though, we have to be very careful the way we write it. So you have to have the variables on the left and the constants on the right, like I've done this. Because once you translate that into the matrix, if you don't have it in that form, everything's going to get goobered up and you don't actually get the right answer. And the variables need to be in the same column. Like, it doesn't matter whether the s's are first or the t's are first, but I have to have like the t's all in one column and the s's all in another column. Is that okay? Okay. As I mentioned before, I have 3 equations here, but only 2 variables. So to solve my system, I'm just going to pick 2 of the 3 equations. I picked the first 2. When I solve that system in my calculator, I just made a matrix and did the RREF thing that we've done before. I get t is -2 and t is +2 and s is -2. And when I plug those into the third equation, it does check out. I get the same thing. So I know that, yes, there is an intersection. Everybody okay with that? Because the system had a solution, and when I check that solution in the third equation, it checks out. So the last thing I need to do is to find that point of intersection. So I'm just going to pick either the S or the T. It doesn't matter which one. I chose the T. And plug it back into the corresponding equation. So since I picked T, I'm going to plug it into R1, because R1 had the T in it. And when I do that, 2 plus 4 times 2 is 10. 4 plus 5 times 2 is 14. And 1 plus negative 3 times 2 is negative 5. That's not negative 5, though. Oh, yeah, it is negative 5. Okay with that? So, for example, if there was the non-parallel, non-intersecting, either the solution you solved, you would have gotten a no solution. So, like one row of your matrix would have been 0, 0, and then like a 1. That's a no solution situation because you have 0s plus 0t equals a constant. So basically 0 equals 1. Or when you check the S and T you got in the third equation, doesn't check out. So either one of those two things could happen. That would tell you that there is no intersection. What you have is the non-parallel, non-intersecting. And in the situation where the lines were parallel, if when you're plugging the point vector in to one line and you solve for the T or the S respectively, if one of those disagrees, or more of them, I guess if they could all be different, but if they're not all the same value, then it tells you that the point isn't on the line, so that would just be straight parallel, not the coinciding. Does that feel a little bit better? And just kind of reviewing what the process is and what we're doing here. It's one of these that, like, if you're not real good on these little subroutine operations that we've been working on, this can be kind of, feels really a lot worse than it really is. But these are all things that we've done, right? We spent some time in class already looking at finding the intersection of two lines in 2 dimensions, right? We spent time checking to see if a point is on a line in 2 and 3 dimensions. Those are basically the two things that you're checking after you do the scalar multiple test, which is like super easy. Is that better, worse, same? Better? Okay. So how many of you guys tried the 119 through 122 like I asked you to do? Okay. Blake? Oh, you're just saying you did.
Oh, yeah, sorry. I did have a question.
Yeah, go ahead.
So, I'm just kind of confused if, like, okay, so how can, like, a line be not parallel but then also not intersect at the same time?
Okay. So the picture, because you have 3 dimensions, so like line M is in this plane here, line N is in this plane up here, and there's not like some third plane you could draw that would be able to capture both of those 2 lines at the same time, where they could be parallel.
Okay.
Right?
Yeah. Okay.
Like I think in geometry we called this skew. I think was the term you used in geometry, if you remember back that far, but that sounds familiar to me, or sounds right. But that's how it can happen, is because you have the third dimension. Because a line is a 2-dimensional object, right? So like if I have a line here and a line up here,
yeah, they don't
like
cross, but they're not.
They're not crossing, but they're not parallel either, because this is going this direction, this is going that direction. What are they?
Yeah.
They're non-parallel, non-intersecting. Does that?
Yeah, that does make sense. Yeah.
Yeah, sure. Did you want to talk about one of these homework problems in particular here? Anybody? Nat?
I got up to 119, so can we do 119?
Sure, of course. There we go. Okay. So the first thing we'd want to check is to see if they're parallel. So we're going to take the direction vectors and see if one direction vector is a scalar multiple of the other. So basically all I'm doing is I'm just solving 3 separate equations, one for each component. And when I do that, I get the same value for k. Each time I get 2/3. Does that feel okay, Nat? Okay. So, yes, these lines have parallel direction vectors, or the same direction vector ostensibly. So the next thing I'm going to check is to see if they're coinciding. So to do that, I'm going to take the direction vector from one of them and plug it into the other. I'm sorry, the point vector from one and plug it into the other. And what I'm going to do there is I'm going to take each component and make an equation. So I have the x component. I have the y component. And then I have the z component. And now I'm just going to solve for each of them. So I'll subtract the 2 over and then divide by 9. I'll subtract the 5 over and then divide by 6. And right here I would stop. You could keep going, but I'm going to stop because already the b's are different. So it tells me that they're not those two lines can't coincide because they don't have every point in common. So I would say that these lines are just parallel. Does that feel okay? So again, it's one of these things like you just have to really be cognizant of what you're doing. If you think about what it is that this is really doing, it really makes sense, the test that you're doing and what you're checking. Sometimes it's easy to get bogged down in like the actual arithmetic. But I think for me, taking a high level view here of like, okay, what am I really doing here? I'm just checking to see if a point from one line lies on the other. Okay, if I'm just checking to see if these two lines, have parallel direction vectors, or if these two lines intersect. If you think about it kind of in that way, it's like, okay, the outcomes make sense about what you're doing. If you have two things that are parallel and they don't have any point in common, or two parallel, the direction vectors are parallel anyways, but they don't have anything in common, it's like, okay. Anyways, does that feel better? Cool.